let's review mechanical properties. If you're applying a force to a part, it's not just the force is important, but also the geometry. So, for example, if you're applying a force pulling on a part, the cross-sectional area is also important. And we say that the stress being applied is equal to the force divided by that area. We call this the engineering stress because we just take the initial area, and over time that's going to slightly change, but that gives us the true stress is one that changes in time. And you'll see that at some other point. But for now, just the engineering stress is important, and that's in fact what most of the time we work with. If instead of applying the force normal to the surface, we apply the force tangential to the surface, then we are shearing the material and we get a shear stress. And again, the shear stress is proportional to the force divided by the cross-sectional area that we're applying the force to. After some force has been applied, the material changes shape. If we're shearing it, we get kind of a skewing. If you imagine having a deck of cards and you push that deck of cards, you're going to have a skew to that, and there's an angle that it skews. The angle that it skews tells us the shear strain. The shear strain is equal to tangent of that angle. Applying a normal force, we change the length of the material from L0 to L, and the strain is equal to the change in the length divided by the initial length. And again, these are called engineering stresses and engineering strains. Notice that if we're pulling it in what I'm calling the Z direction, that it elongates in that Z direction. So I put a little subscript Z. In the X direction, which is perpendicular to the force being applied, it's going to contract. And you know this anytime you pull on a rubber band, you see the rubber band stretches and it contracts. So that is a contraction in the X direction. And we have what's called the Poisson Ratio, which is minus the strain in the X direction divided by the strain in the Z direction. And that tells us about, for a given amount of elongation in Z, how much does it contract in the other directions. And that's called Poisson Ratio, and we used a nu, Greek letter nu for that. If we're applying a stress, and we look at the strain as the stress is being applied, we start out with basically a linear change in the length. And that linear change is happening during a period we call elastic deformation. And during that elastic deformation, we say that the material obeys Hooke's law. And Hooke's law is that the stress is equal to the elastic modulus multiplied by the strain. So the elastic modulus is the slope of that curve in the elastic region. The elastic region continues up until we reach what's called the limit of linear proportionality. That's the place where it starts to deviate from being linear. And that, strictly speaking, is the place where we move from elastic deformation, which is just the stretching of bonds, to plastic. And in plastic, we have a permanent breaking of bonds or shearing of atoms across each other. And when you release the stress, those broken bonds don't go back together. You can only restore bonds that have been stretched but not broken. So that proportionality limit is the place where we transition and we start doing permanent damage, called plastic flow. Unfortunately, it's very difficult to measure that. And as a result, instead of the limit of proportionality, we typically talk about what's called the yield point or the yield strength. And if you pull a curve, and then you go back and you look at the point where we see an offset from linearity by 0.002, or we also use percentages, so we call it 0.2%. That 0.2% and we go up to where that stress is. Well, that stress is our yield point. We keep pulling, we keep doing plastic deformation, we reach the maximum point of the curve, and this is called our ultimate tensile strength, or the tensile strength of the material, and we keep pulling, and eventually it fails because the part breaks. So this is kind of the general shape, and some curves are more elongated than others. Some have a really long period of plastic deformation. For example, a very ductile material like a metal, lead, is going to have a really long plastic deformation. In contrast, some, they have almost no plastic deformation. For example, glass. You pull on a glass and pull, it might move a little bit elastically, and then it pops and it breaks. So it goes straight from elastic into fracture. And those are brittle materials. So the shape of this curve tells us a lot about the nature of the bonds and the material's performance when it's going to be used. This elastic modulus is sometimes called a Young's modulus, and we have Hooke's law for linear elastic tensile loading. But if instead of tensile loading we're applying a shear, that also obeys Hooke's law, and now we say that the shear stress is equal to the shear modulus multiplied by the shear strain. So that G is the shear modulus. And the good news is when we're talking about isotropic linear elasticity, meaning we're treating the material as though if I pull in any direction it behaves the same, then we have a relationship between shear modulus, Poisson ratio, and the Young's modulus. And there's another elastic constant called the Lemay constant that we're not talking about here, but that's also another one that we can use to relate all of these to each other. As I said, this is linear elastic isotropic materials. If you think about, instead of talking about just a generic material, not generic, let's call it a polycrystalline material, so all the directions are the same because we have lots of different crystals all aligned differently. Let's say you have a single crystal and you're pulling on it, well then you know, because of the way it's bonded, that pulling in one direction versus another is going to be slightly different because of the way the bonds are aligned. And in that case, you talk about anisotropy. And anisotropy is something that we're not going to talk about in this class, but you should know that isotropic versus anisotropic are different. And the real difference is in something that's anisotropic, you're oftentimes thinking of a single crystal, or thinking of a crystal where all the material where all the polycrystals are aligned in some way. For example, when you're making a wire, you're drawing a wire through a die, and that's going to cause the crystals to line up in certain directions. So a wire, pulling on it in the direction of the wire versus perpendicular to the wire length, oftentimes the mechanical properties are different. And then lastly, we talked about situations in which we would start applying a load and then reverse the load. So we have this elastic regime, and when we start moving into plastic, if we stop and we unload the material, then we're going to reverse. And what we're reversing is essentially where some of the bonds are stretched and some of the bonds are broken. Well, the bonds that are stretched, they can go back together. The bonds that are broken are permanently stuck. So if you start loading material and at some point you stop and then you release, well, where you release, the broken bonds stay. So this is your permanent plastic damage or plastic deformation, and the elastic part is restored. And if you take that and you start loading it again, well then what happens is it goes straight back up that original line, and then it continues. So that plastic deformation stays, and as you reload, you just start accruing more plastic damage, and it will eventually trace out a curve the same as this one. And lastly, I also want to talk a little bit about this upper and lower yield point. Sometimes materials have this where you will be loading, and you have this elastic deformation, and then all of a sudden it starts to deform, and when it does that, it takes less force to load it, right? That's telling us the force that we need to apply to get a strain. And you have this drop in the force necessary for plastic deformation. And what's happening, and we'll talk about this a little bit in this class, is that you have defects in the material that are helping with the plastic flow, and they suddenly become active, and when they start moving, then the flow is much easier. So it's kind of like that initial point where you overcome the internal friction inside the material for these deformation mechanisms, and once they start, then it's easier. And this is what we talked about in our class.